Welcome everybody. My name is K.Pomorski and I would like to give a talk on a semiconductor-superconductor quantum hardware. So the full title of my talk is Universal Modeling of Electrostatic Semiconductor Quantum Gates of Any Topology Interface to Josephson Junction Quantum Circuit. So this is work done by Quantum Hardware Systems Company also affiliated also to Krakow University of Technology. So outline of my talk is as follows. So I would like to at first describe the current status of quantum technologies, and then I would like to give definition of semiconductor single-electron qubit. Then I would like to mention something about topological protection of the quantum information. I also point how to construct quantum neural networks using chain of coupled quantum semiconductor dots. And then I would like to give some outline on programmable quantum matter. This will be due to possibility of controlling quantum graph topology of quantum graphs. And this topology can be controlled in an electrostatic way. At the very end of my talk, I will mention about a case of two interacting single-electron lines. And I will also point the possibility of construction of hybrid semiconductor superconducting quantum computer using the Josephson junctions interfaced with a chain of coupled semiconductor quantum dots. And it will turn out that such systems are topologically protected, as you will see after a few slides. All right, so what's the current status of the quantum technologies? There's more than 20 possible approaches how to construct a qubit. However, our interest focus on high integration scale or medium integration scale. And we also want to be, we also want to fit the already existing technologies, and I mean mostly semiconductor devices, field effect transistors that has very large integration scale. So because of that, I will promote only two technologies. One is based on superconductors, one is relying on semiconductors, and then I will point the construction of the interface. All right, so what's the scheme of single electron devices approach in implementation of qubit? So we can construct electrostatically controlled qubit. First experiments in this direction was done by Fujisawa and Peta in 2004. So essentially the quantum information is encoded in quite different way. So we inject electron into one among two quantum dots that are coupled, that are connected, and this electron wave packet will tunnel back and forth. So we have characteristic oscillations of presence of electron, and the presence of electron on one quantum dot will encode 0, and presence of electron on another quantum dot will encode 1, and in general case we have a superposition of two states as we are dealing with quantum mechanical phenomena. And when we want to obtain the quantum entanglement, we need two coupled single electron lines, and then the entanglement between those two qubits emerges as coming from electrostatic interaction between those two electrons. So the scheme of semiconductor qubit interfaced to Josephson junction is depicted here. So we have a Josephson junctions described as superconductor, non-superconductor, superconductor state, and then there is a quantum dot system that is depicted here. So we have a quantum dot 1 and 2. So in such type of system, the moving electron from quantum dot 1 to 2 back and forth generates time-dependent electric field and time-dependent magnetic field. And this field imprints unbound states in Josephson junction. So this interaction is very subtle. But still we can obtain entanglement between those two systems. And further, it will turn out that those systems are also topologically protected. All right, so we can generalize the scheme describing the interface between Josephson junction and semiconductor quantum dot system. So on the right picture, I already depicted Cooper pair box Josephson junction, and there is a single electron device, the semiconductor single electron device that is given here. So there is this electrostatic channel of interaction. So this system interacts with this Josephson junction. Also, this system interacts with this Josephson junction. So scenario 2 is about electrostatic channel of interaction between semiconductor and superconducting system. However, scenario 1 describes the interaction between flux Josephson junction qubit with a ring, a semiconductor ring, a kind of roton-like structure. So we have moving electrons on this closed path are generating quantized magnetic flux that enters the flux Josephson junction. And then, so those systems interact by magnetic field. However, in general case, we can combine those two mechanisms. So this is very promising scenario for construction of hybrid superconducting semiconductor quantum computer. So that essentially interconnects semiconductor quantum chip with superconducting quantum chip. We can also have the possibility for a quantum communication between semiconductor quantum dot systems. So we have a one qubit which is given here that interacts with a quantum electromagnetic cavity. There's exchange of photons, and this furthermore this resonant cavity is interacting with another qubit. So it can what it turns out there will be entanglement between those two systems. This is induced from entanglement between first qubit and resonator cavity and another qubit and resonator cavity. So this is very also promising concept for a quantum communication. So furthermore, we can, referring to the previous concept of two interacting qubits via quantum resonant cavity, we can think about topological protection of a quantum information. So we can use Berry phase concept, and in such case, the coherence time of such system is much longer than without using those concepts. So that's also quite promising direction of development. So we can, due to current stage of development of nanotechnologies, we can construct various zoo of topologies of chain of coupled semiconductor quantum dots. You can see various shapes. And also we can control the state of qubit by placement of special voltage to the bar that is on the top of two quantum dots. So this will control connectivity between quantum dots. So you can functionalize those structures for various type of quantum information processing. So using the concept of coupled semiconductor quantum dots, you can also create neural networks. So if you have the quantum dots depicted with red color, and then there's the voltage gates that controls connectivity between quantum dots with a gray color, then you can inject like free electrons And then you can, when they travel via the structure, they arrive to certain detectors. So you can get certain entanglement between them, and you can utilize special voltage dependence with time, so you can obtain certain quantum operations. So you can also build the quantum neural network with many layers. You also can turn the magnetic field to help in this quantum information processing. So this scheme allows you for creation of quantum neural networks that has very small dimensions. All right, so I have already mentioned about the case of control of connectivity between quantum dots. So basically the presented concepts allows you to have a couple, to have a topology of, to control topology of quantum graph constructed from semiconductor quantum dots, and then you can implement various quantum algorithms using this structure. So there is a very rich family of possible topologies of semiconductor qubits, let's say Vannier qubits, you can see here. And then there's quite important to recognize already presented concept in the context of already existing quantum technologies. So most existing quantum technologies allows use of the eigenenergies and eigenfunctions of those eigenenergies to encode quantum information. So basically we deal with eigenenergy qubit mostly, but we can convert this eigenenergy information encoded in eigenenergies into Vannier qubit. So we use a concept of maximum localized wave functions on the left and right quantum dots. And then there is a presence of electron on one of the quantum dot system, another quantum dot system, and then there is some hoping terms and that you can recognize here. And actually you can get a very simple formula how to get these hoping terms using the Schrödinger equation that's depicted here. So then you can translate this information from one system to another system. All right, so already we can move further, and we can deform Vannier qubits. So we can use nanowires, and using such coupled nanowires, we can also encode the quantum information processing. It can also turn out that there's no need to use a voltage to control the connectivity between quantum dots, but you can use also geometry. That's quite a remarkable feature. And having two coupled quantum dots, you get coupled Schrödinger equations that interact electrostatically. It's given here. And so that's also, you can also actually model the behavior of Schrödinger equation in a curved space from certain perspective. So as about referring to topologically protected qubits occurring in interface between Josephson junction and semiconductor Vannier qubits, well, controlling the order parameter, superconducting order parameter, it turns out that we observe quantum phase transition, and that excited states are exchanged in position with the ground states. So this is a very promising feature for topological protection of a quantum information. Yeah, so there are various work described in more detail, referring to presented concepts. So that's, you can find here and here. And also there is a framework for future activities that is outlined here. All right, so thank you for your attention, and I welcome some questions.